I mentioned in the last several videos that the coefficient of kinetic friction tends to be less. Sometimes it'll be roughly equal to the coefficient of static friction. But this might lead you to at least a question that I've had in my mind, and I still have to some degree, is why is the coefficient of kinetic friction lower? Or why can it be lower? And the current best theory that I can visualize in my head and based on the reading that I've done is the difference between. So let's think about it this way. So if we look at it at a kind of a regular human level, maybe we have a block. Maybe we have a block. So this is the static case. So let's think about the static case over. Let me draw it like this. So I'll draw the static case over here. So I have a block that is stationary on top of, let me do the surface in a different color, on top of some type of surface right over here. And over here, I'm going to have a block moving at a constant velocity, relative to some surface, relative to the same surface. And so let me draw it out. So this is moving at some constant velocity, constant velocity. And so the interesting thing here is, assuming that these are the same masses, that these are the same surfaces, is why should the coefficient of friction here, why should the coefficient of static friction, so here, since this is stationary, what's under play is the coefficient of static friction. Why should that be larger than the coefficient of kinetic friction over here? Why should that be larger than the coefficient of kinetic friction? Or another way to think about it is, you would need to apply more force to overcome the static friction here and start to get this accelerating than you would need to apply to get this already moving body to accelerate, because there would be kind of a less of a responsive friction force. So let's think about that a little bit. So what I'm going to do is zoom in into the atomic level. And so when you zoom into the atomic level, almost nothing is completely smooth. So this surface over here might look something like this. So I'm going to draw the molecules that make up the surface. So the best to my ability. So the molecules, when you zoom up really close for the surface, might look something like this. And when you, we're really zooming into the atomic level, unimaginably small level, much smaller than that box I just drew. But I'm just trying to look at what's happening with the atoms where they contact, or the molecules where they contact. And the box's molecules might look something like this. The box's molecules might look something like this. They aren't completely smooth. They aren't completely smooth. And hopefully this video also emphasizes that all of these forces and all of this contact that we're talking about in these videos, and it's actually interesting philosophically, nothing is ever really in contact with each other. You really just have atoms that are repulsing each other because they're electrons. The electromagnetic force of repulsion between them is not allowing them to get any closer together. So that's all. When you push something, it's just the electrons in your hand pushing on the electron, or the electron clouds in your hand, pushing on the electron clouds of, say, the pen you're holding, or the key on your keyboard, or the mug, so that it repulses and causes it to go in the other direction. So that there's never any this thing like real, what we imagine in our heads, real contact. And if you really want to blow your mind, and watch the chemistry videos if you want to understand this, is that most of these atoms are actually free space themselves. That the electron cloud is huge relative, or I guess where most of the probability of finding the electron is huge compared to the size of the electron or the size of the nucleus. So it's kind of just a lot of free space pushing on a lot of other free space through the electromagnetic force. But anyway, we're talking about friction here. So if you were to really zoom in here, when this thing is stationary, you have the surfaces aren't actually even. And so you can imagine that these molecules that you have, sometimes when it's sitting stationary, they might be kind of fit into each other. They've kind of slid into maybe these little ruts here and there. And so if you're trying to move this object, if you're trying to accelerate it to the left with some force, you have to overcome essentially either for example, this part right over here either has to somehow break off, or the whole thing has to be shifted up a couple of atoms or a couple of molecules, or maybe this part over here has to be broken off or has to be shifted down one atom. You wouldn't notice these things. You wouldn't notice the shifting of a block or the shifting of the floor. You wouldn't notice it by the width of a molecule or diameter of an atom or a molecule. But that's essentially what you're going to have to do, or you have to rip them off entirely in order to start this thing moving. Once something is already moving, and this is at least how I think about it, a lot of it doesn't have a chance to settle into these little ruts. So let me draw something that's already moving, and I'll try to draw a similar surface. So I'm trying to draw the surface that looks essentially just like the one I drew. So maybe it looks like that. They're supposed to be the same surface. But once it's moving, it's kind of it's not sitting in these ruts anymore. The whole thing is moving, so it's kind of sliding across the top. And so now it might look something like this. I'm trying my best to draw it. So now it might look something like this. Maybe this has been shifted up a little bit so that it can start sliding. You've overcome overcame the static friction. So now it is. So let me draw the same. I'm trying to draw the same surface here, so give or take. So now it's moving. It doesn't have a chance to really settle in. It has to kind of bounce along the top. And so that's the best understanding. And so the real force of the friction here, there will be still some, as it's moving along, it still might every now and then bounce into little ruts here and there. But you also have any type of chemical bonds that form between the atoms temporarily that keep breaking and forming. And in order to keep this thing, for I guess moving, or especially if you want to accelerate it, you're going to have to keep breaking these bonds. And so that's essentially the force of friction that you're overcoming. Here, you might have those same bonds, and not only do you have those same bonds, but you also have to overcome these ruts, or these little ragged parts that have a time to settle into these little nooks that you have to overcome even more. So that's the intuition. And this is actually still an area of research. So it's not like this cut and dry thing. And it's a fun thing to think about what's happening at the atomic level. But this is the general intuition of why the coefficient of static friction is higher than the coefficient of kinetic friction.